In the deepening twilight, a shadow detaches itself from the ancient forest canopy. It moves not with a rush of wind or a flurry of wings, but with an eerie, profound silence. This is the realm of the owl, a creature often seen as a symbol of wisdom, yet in the natural world, it embodies something far more primal and formidable, the perfect assassin. Tonight, we delve into the extraordinary science behind their lethal efficiency, exploring how evolution has forged a hunter unparalleled in its specialized craft. The term perfect assassin might seem hyperbolic, but when we examine the intricate suite of adaptations owls possess, it becomes evident why it's a fitting descriptor. From their unique feather structure to their sophisticated sensory organs, every aspect of an owl's physiology appears fine-tuned for a single purpose: effective predation. Our investigation begins by asking, what specific evolutionary pressures led to such a precise and specialized hunter, and what evidence supports this claim of perfection? Most owl species are predominantly nocturnal, a strategy that, according to behavioral ecologists like Dr. Elena Petrova from the Institute of Avian Studies, significantly reduces competition with diurnal raptors such as hawks and eagles. This temporal niche allows owls to exploit prey that is active or vulnerable under the cover of darkness. This initial strategic choice, the shift to night hunting, appears to be the foundational step that drove the evolution of their remarkable sensory and physical adaptations. Perhaps the most iconic and crucial adaptation of an owl is its ability to fly in near-complete silence. Imagine a predator moving through the air, inches from its prey, without a whisper of sound. This incredible stealth is not merely a beneficial trait, it is, as biomechanical engineers from the University of Cambridge have demonstrated, a complex triumph of aerodynamic engineering. Their studies indicate that this silent flight capability is the cornerstone of their ambush hunting strategy, allowing them to approach undetected. Research published in Journal of Experimental Biology highlights 3 distinct features in an owl's wing feathers contributing to this silence. First, the leading edge of an owl's primary flight feathers is serrated, like a comb. This unique structure, according to the research team led by Dr. Martin Hughes, breaks up the airflow into smaller, less turbulent streams. Conventional bird wings generate noise from air rushing over a smooth leading edge, creating vortices. Owls mitigate this at the very first point of contact. Secondly, the surface of an owl's flight feathers is covered in a fine, velvet-like down. This isn't just for insulation. Dr. Hughes's team postulates that this down acts as an acoustic absorber, damping any residual sound produced by the air moving over the wing surface. It effectively creates a sound-absorbing barrier, further muffling the already reduced turbulence. This dual-purpose adaptation showcases an elegant solution to the problem of noisy flight, turning a potential disadvantage into a formidable weapon. Thirdly, and perhaps most subtly, the trailing edge of an owl's flight feathers features a flexible fringe. This fringe, often described as a comb of soft bristles, works to smooth out the airflow where it leaves the wing. Instead of the abrupt separation that creates turbulent eddies and noise in other birds, the fringe ensures a gradual, controlled rejoining of air. This minimizes the vortex shedding that generates significant aerodynamic noise, completing the trinity of adaptations for silent flight. To quantify this silence, bioacoustic studies have compared the sound profiles of owls against other birds of similar size, such as pigeons or even other raptors like falcons. The results, consistently reported across various research groups, show that owls generate sound levels at least 15 to 20 decibels lower than their counterparts during flight. This reduction is profound, rendering their approach virtually inaudible to most prey animals, especially in the ambient noise of a natural environment. This extraordinary silent flight allows the owl to achieve complete surprise. A small rodent, relying on its keen hearing for survival, would simply have no warning. The owl descends, a feathered specter, its approach masked by the very air it displaces. This stealth negates a prey animal's primary defense mechanism, detection, making the owl's initial strike incredibly effective. Without this silence, many other adaptations would be far less potent. Once within range, the owl must accurately locate and target its prey, often in conditions of minimal light. This brings us to the second pillar of their predatory perfection, their vision. Owls possess eyes that are disproportionately large relative to their skull size, a fact consistently observed in comparative anatomy studies. These ocular organs are not merely big, they are profoundly specialized instruments designed for superlative low-light performance, crucial for their nocturnal lifestyle. Unlike human eyes, which are spherical, an owl's eyes are largely tubular, fixed in their sockets. This peculiar shape, as described by ocular biologists, allows for a greater concentration of light-sensitive cells. The fixed nature of the eyes means owls cannot roll them, yet this is not a limitation. Instead, it permits the eye to be larger and more effective at gathering ambient light, especially from distant sources. This trade-off emphasizes specialization over versatility. The retina of an owl's eye is densely packed with rod cells, far outnumbering the cone cells. Rods are responsible for detecting light and motion in low-light conditions, while cones perceive color. Ornithological research indicates that some owl species have up to 5 times the rod density of diurnal birds. This means their eyes are incredibly sensitive, allowing them to discern faint outlines and movements even under starlight or overcast skies, where other predators would be effectively blind. Crucially, owls possess binocular vision, meaning both eyes face forward, providing overlapping fields of view. This overlap is vital for excellent depth perception and the ability to accurately judge distances, a prerequisite for a precision strike. While their peripheral vision is limited due to fixed eyes, the accuracy gained in their central field of view, as noted by studies in spatial perception, is paramount for targeting fast-moving prey in complex environments. Given their fixed eyes, how do owls navigate and scan their surroundings? The answer lies in their astonishing neck flexibility. Owls can rotate their heads up to 270 degrees in either direction, a total sweep of 540 degrees without moving their body. This extraordinary range of motion, supported by 14 cervical vertebrae, compared to 7 in humans, and specialized vascular structures, compensates entirely for their lack of eye movement. They literally turn their head to bring their binocular gaze to bear. While their night vision is exceptional, it's important to note the trade-offs. Owls generally have poor color vision compared to diurnal birds and humans, and their farsightedness means objects very close to them can be blurry. However, for a predator swooping down from a perch, these are minor limitations. Their visual system is optimized for detecting subtle movement at a distance in low light, precisely what is needed for nocturnal hunting, as behavioral studies consistently affirm. In the darkest nights, when even their superb vision might struggle to penetrate the gloom of dense undergrowth, owls rely on their third, equally astonishing adaptation, hearing. Many owl species can pinpoint the exact location of prey by sound alone, even if the prey is completely hidden under snow or vegetation. This auditory precision, meticulously mapped by neurobiologists, transforms the dark forest floor into an acoustic landscape, revealing every rustle and squeak. A distinctive feature of many owl species is the facial disc, a concave arrangement of stiff feathers that frames their face. This isn't merely decorative. Research from the University of Maryland's Auditory Neurobiology Lab has confirmed that this disc acts as a highly effective parabolic reflector, funneling sound waves directly to their ears. It dramatically enhances their ability to capture and amplify faint sounds, much like cupping a hand behind an ear, but with far greater efficiency and natural design. Beneath this facial disc lies an even more remarkable adaptation: asymmetrical ear openings. Unlike most birds, one ear opening on an owl's head is often higher or larger than the other. This asymmetry, extensively studied by neuroscientists, is the key to their extraordinary spatial hearing. Sounds reach each ear at slightly different times and with varying intensities. The owl's brain processes these minuscule differences to construct a precise, three-dimensional acoustic map of its environment. The brain of an owl is exceptionally adept at processing these subtle auditory cues. Studies, notably by Dr. Eric Knudsen at Stanford University, have detailed how barn owls, in particular, possess a specialized neural pathway dedicated to sound localization. This pathway allows them to resolve directional differences of less than 1 degree both horizontally and vertically. It is this neural sophistication that translates the raw auditory data into an exact targeting solution, even in absolute darkness. Imagine the synergy. Silent flight allows proximity, unparalleled vision confirms the target in dim light, and acute hearing provides a continuous, precise fix on its exact location. These sensory systems don't operate in isolation, they integrate seamlessly. If an owl's vision is obscured, its hearing takes over with astonishing accuracy. This redundancy and fusion of senses create an almost foolproof detection system, significantly increasing hunting success rates, even in challenging conditions. With the target identified and approached silently, the final act of predation relies on the owl's physical tools for capture and kill. This brings us to the fourth pillar of their assassin-like prowess, their formidable talons. An owl's feet are masterpieces of evolutionary design, built for maximum grip and lethal force. Comparative studies of raptor anatomy highlight distinct differences that empower owls to subdue prey swiftly and decisively. Most raptors possess anisodactyl feet, with 3 toes forward and 1 backward. Owls, however, are typically zygodactyl, meaning 2 toes face forward and 2 face backward. This arrangement, according to studies on avian foot morphology, provides a much wider and more secure grip. It allows them to effectively hug their prey, distributing pressure evenly and preventing escape, especially important for slippery or struggling victims. Each talon is needle-sharp and robust, capable of piercing thick hide and bone. But it's not just the sharpness, it's the sheer crushing power. Biomechanical analysis has shown that larger owl species, like the great horned owl, can exert hundreds of pounds per square inch of pressure with their talons. This immense grip is often enough to quickly dispatch prey, either through direct trauma or by constricting vital organs, as field observations of successful kills confirm. Furthermore, owls, like many raptors, possess a unique locking tendon mechanism in their feet. Once their talons grip, these tendons automatically lock, allowing the owl to maintain a vice-like hold without expending constant muscular effort. This is crucial for carrying prey, but also for maintaining a secure grip on a struggling animal during the initial moments of the kill. Ornithological anatomists confirm this allows for an incredibly secure and energy-efficient hold. Complementing the talons is the owl's powerful, hooked beak. While not used for the initial capture, it is essential for dismembering and consuming prey. The sharp, curved upper mandible acts like a cleaver, allowing the owl to tear flesh into manageable pieces. This ensures efficient consumption, reducing the time spent vulnerable on the ground and maximizing nutrient intake from their kills, as diet analyses of owl pellets frequently demonstrate. Beyond their remarkable physical adaptations, owls also employ sophisticated hunting strategies. They are primarily ambush predators, often perching silently for extended periods, conserving energy while scanning or listening for prey. This patience, combined with their sensory prowess, allows for maximum efficiency. Studies on owl hunting behavior show that they will wait for the perfect moment, ensuring a high probability of success for each strike rather than expending energy on risky chases. Once prey is detected, many owl species engage in a low-level flight approach. This minimizes the silhouette against the night sky, further aiding stealth. They often sweep across fields or through forest undergrowth, their silent flight giving them an unparalleled advantage. Ornithological field guides describe this as a phantom flight, where the owl appears and disappears with uncanny speed and silence, closing the distance to an unsuspecting target. The culmination of all these adaptations is the precision strike. With talons extended forward, eyes locked on target, and silent wings providing stability, the owl descends with remarkable accuracy. Motion capture studies reveal that the final moments of a strike are often incredibly rapid, measured in mere fractions of a second. This speed, combined with the power of their talons, leaves prey little to no chance of escape or counter-defense, solidifying the owl's role as a top-tier predator. While the fundamental hunting mechanisms remain consistent, the actual diet of owls varies significantly across the more than 200 species globally. From tiny elf owls consuming insects to powerful great horned owls preying on rabbits, skunks, and even other birds, their adaptability is broad. However, the underlying principles of silent, sensory-driven ambush predation, as confirmed by countless diet studies through pellet analysis, remain a constant across this diverse group, proving universal efficiency. The fossil record, though sparse for such fragile creatures, indicates that owls have existed for tens of millions of years. This longevity, according to paleontologists, is a testament to the evolutionary success of their specialized predatory design. They have weathered significant environmental changes and outcompete many other avian predators in their niche, largely due to this finely tuned set of assassinating adaptations that remain effective across various ecosystems. The popular image of an owl often focuses on its perceived wisdom or enigmatic nature. Yet, our investigative journey reveals a creature far more defined by its pragmatic, almost ruthless efficiency as a predator. The elegance of its design is not for aesthetic appeal, but for absolute lethality. This underlying reality, though perhaps less romantic, provides a deeper appreciation for the wonders of natural selection and the intricate balance of the wild. Far from being a mere harbinger of mystery, owls play a crucial ecological role. As highly efficient predators of small rodents and insects, they act as natural pest controllers in agricultural and natural environments. Studies conducted by conservation biologists have consistently shown that healthy owl populations can significantly reduce crop damage and disease transmission by limiting rodent populations, often more effectively and sustainably than artificial methods. Furthermore, owls are often considered indicator species. Their presence and health can signal the overall well-being of an ecosystem. Because they sit atop a specific food chain, their decline can point to broader environmental issues, such as habitat loss, pesticide use, or a collapse in prey populations. Monitoring owl numbers provides scientists with valuable data on ecosystem health, making them silent sentinels of the wild, as reported by ornithological surveys. Despite their formidable adaptations, owls face numerous threats in the modern world. Habitat destruction, particularly deforestation and urbanization, removes their hunting grounds and nesting sites. Pesticides accumulate in their prey, leading to secondary poisoning. Collisions with vehicles and power lines also take a toll. Conservation efforts, including habitat preservation, reducing pesticide use, and installing owl boxes, are critical to ensuring these magnificent assassins continue to thrive. Let's consider the barn owl, a widely distributed species, as a prime example of these adaptations in action. Its heart-shaped facial disc is perhaps the most efficient acoustic funnel among owls. Combined with its exceptionally silent flight, it allows the barn owl to hunt in complete darkness over open fields, detecting the faintest rustle of a vole from considerable heights. This specialization makes it a master of its particular hunting niche, as detailed in numerous studies of nocturnal raptors. In contrast, the great horned owl, a larger and more robust species, demonstrates the raw power of these adaptations. Its immense strength and talons allow it to tackle a wider range of prey, from small rodents to larger birds and even skunks, thanks to its less developed sense of smell. Its deep, resonant calls echo through North American nights, signaling the presence of an apex nocturnal predator. It is a testament to the versatility of the owl's core design, scaled for different ecological roles. The snowy owl, a breathtaking creature of the Arctic tundra, exemplifies how all adaptations can be finely tuned to extreme environments. Its dense, insulating plumage provides protection against brutal cold, while its superb vision and hearing are essential for spotting and locating lemmings beneath snow cover in vast, open landscapes. Unlike most owls, it often hunts during the perpetual daylight of the Arctic summer, showcasing a behavioral flexibility within the core assassin framework. Compared to mammalian nocturnal predators like foxes or wildcats, owls possess a unique combination of advantages. Their silent flight allows them to cover ground quickly and stealthily without leaving a scent trail, which mammals cannot replicate. Their superior aerial perspective also provides a broader search area. While mammals have other advantages, the owl's airborne ambush, as ecological comparisons indicate, offers a distinct and often superior hunting niche in the darkness. While feather structure is primary, some researchers, including Dr. Chenley from the University of California, Berkeley, suggest other factors may contribute to an owl's silence. These include body shape, flight patterns, and even the unique way they flap their wings. While less understood than the feather adaptations, these broader aerodynamic factors may subtly enhance the overall stealth, further reducing any potential acoustic footprint during their lethal descent. The combination of silent flight and acute hearing effectively creates a form of acoustic camouflage. Prey animals, accustomed to detecting threats through sound, are rendered vulnerable. This is not simply a lack of sound but an active suppression that manipulates the sensory landscape, turning the owl into a ghost in the night. It is a testament to natural selection's capacity to optimize every detail for survival and predation, as explored in bioengineering research. To fully grasp an owl's vision, consider how it differs from our own. Where our eyes struggle in dim light, an owl's eyes become super-perceptive instruments. The sheer number of rod cells means they are not just seeing a little better in the dark, they are operating in a completely different visual register. This allows them to exploit a hunting window closed off to most other animals, offering a profound insight into the diverse ways life perceives the world. In conditions of absolute darkness, such as within a dense thicket or deep burrow, an owl's hearing becomes the sole, guiding sense. Experiments in controlled environments have shown owls can strike prey with nearly 100% accuracy, relying purely on auditory cues. This highlights the redundancy and robustness of their sensory system. Should one sense be compromised, another is poised to take over with remarkable efficacy, maintaining their lethal edge. The diversity of owl species across the globe underscores the adaptability of these core assassin traits. Whether hunting fish from an Alaskan river, insects in an African savanna, or small mammals in a European forest, the fundamental principles of silent flight, acute senses, and powerful talons are consistently applied. This adaptability confirms that their predatory framework is not limited to a single niche but is a robust, versatile blueprint for success in varied ecosystems. Beyond their active hunting adaptations, owls also employ passive stealth, camouflage. Their cryptic plumage, typically a mosaic of browns, grays, and whites, allows them to blend seamlessly into their natural surroundings. This aids in ambushing prey by making them virtually invisible before a strike and also offers protection from larger diurnal predators. This blend of active and passive stealth further enhances their assassin profile, as behavioral observations confirm. The owl's hunting strategy is also remarkably energetically efficient. By perching, waiting, and executing precise, silent strikes, they minimize energy expenditure compared to predators that rely on extended chases. This efficiency is critical for nocturnal hunters, where opportunities can be sporadic and successful kills must maximize caloric intake. It's a calculated approach that optimizes the metabolic cost of living for a highly effective predator. The sum of these extraordinary adaptations converges to create what can only be described as a phantom predator. Its movements are unheard, its presence often unseen until the final, deadly moment. This mastery of stealth and precision allows owls to exert significant control over prey populations, shaping local ecosystems in profound ways. It's a testament to the power of specialized evolution, crafting an organism perfectly suited to its lethal role. In the intricate tapestry of nature, owls are unseen architects of balance. Their effectiveness as predators ensures the health and vitality of ecosystems by regulating prey numbers, especially of prolific rodents. Without these silent assassins, populations of small mammals could explode, leading to ecological imbalances, disease spread, and agricultural devastation. Their quiet hunts maintain a crucial equilibrium, a fact frequently emphasized by ecological monitoring groups. The owl's legacy is one of survival through mastery. Each feather, every nerve ending, the very structure of its bone and muscle has been sculpted by millions of years of natural selection into a highly optimized predatory machine. From the serrated edges of its wings to the asymmetrical placement of its ears, these are not random features but precision instruments honed for one overarching goal: the efficient, silent, and decisive capture of prey. Our fascination with owls dates back millennia, often attributing them with mystical qualities. Yet, understanding the scientific basis of their predatory success only deepens our respect. It transforms the mystic into the magnificent, revealing not a creature of magic, but one of extraordinary biological innovation. This shift in perspective allows us to appreciate the owl not just as a symbol, but as a living, breathing testament to nature's profound capacity for perfection. So, are owls truly nature's perfect assassins? Based on the overwhelming body of scientific evidence, their unparalleled silent flight, their hypersensitive vision in darkness, their acoustic pinpointing capabilities, and their powerful, specialized talons, the answer appears to be a resounding yes. Each adaptation is a chapter in a biological textbook, detailing a predator so exquisitely evolved that it stands as a pinnacle of nocturnal hunting prowess. These silent guardians of the night continue their ancient vigil. From the smallest elf owl to the mighty great horned owl, they navigate the darkness with an efficiency that commands awe. Their story is a powerful reminder of the relentless ingenuity of evolution, shaping life into forms that are both beautiful and brutally effective. The next time you hear a hoot in the darkness, remember the complex, silent ballet of the assassin unfolding in the shadows. The evolutionary pressure for stealth in owls is directly linked to the survival of their prey. Animals like voles and mice have evolved acute hearing and a strong flight response. To overcome these defenses, owls developed mechanisms to virtually eliminate detection. This biological arms race between predator and prey ultimately drove the sophisticated development of silent flight, pushing acoustic boundaries to their absolute limit, as detailed in evolutionary biology texts. Beyond silence, an owl's dense plumage offers exceptional thermal insulation. For a nocturnal hunter, maintaining core body temperature during cold nights is vital for peak performance. This efficient insulation, while not directly tied to hunting, indirectly contributes by allowing the owl to remain active and agile for longer periods in chilly conditions, ensuring that its predatory tools are always at optimal readiness, as physiologists confirm. The wing design of owls also accounts for their relatively large body size compared to some other birds of prey. Their broad wings with a low aspect ratio contribute to a low wing loading, meaning less weight per unit of wing area. This enables slow, controlled flight and easy maneuverability, which is essential for navigating dense environments and making precise adjustments during a strike, according to avian aerodynamicists. You might observe an owl head wobbling or bobbing its head. While sometimes misconstrued as confusion, this behavior, according to behavioral neuroscientists, is actually a sophisticated technique for enhancing depth perception. By slightly shifting its head, the owl creates parallax, allowing its brain to calculate distances more accurately to a stationary or slow-moving target, particularly useful before a strike, especially when relying on auditory cues. While silence defines their hunt, owls possess a wide array of vocalizations beyond the stereotypical hoot. These calls serve various purposes: territorial defense, attracting mates, and communication between parent and young. Each call is specific, signaling different intentions within their complex social structures. This vocal repertoire, while not directly used for assassination, is vital for the social dynamics that support their solitary predatory lifestyle, as bioacousticians report. One of the most valuable sources of data for understanding owl diets and hunting prowess comes from owl pellets. These regurgitated masses contain the indigestible parts of their prey: bones, fur, feathers, and teeth. Analyzing pellets provides an invaluable forensic record of what an owl has eaten, allowing scientists to reconstruct diet preferences, hunting success, and local prey populations, offering direct evidence of their role as assassins. The owl's mystique, for centuries, has shrouded its true nature. But through the lens of scientific inquiry, we see not merely a creature of myth, but an exquisitely engineered biological mechanism. The owl remains, yet it shifts from supernatural wonder to a profound appreciation for evolutionary design. It is the story of how millions of years of refinement can produce a predator so specialized, so efficient, that it embodies the very concept of a perfect assassin. Consider, for a moment, a world without owls. The ecological repercussions would be vast. Rodent populations could spiral out of control, leading to agricultural crises and rapid spread of disease. The subtle balance maintained by these nocturnal hunters would be catastrophically disrupted. Their absence would highlight just how indispensable these perfect assassins truly are to the health and stability of our natural world, as ecological models predict. The future of the owl, and indeed, the future of many ecosystems, lies in our hands. Understanding the intricate biology that makes them such effective predators should inspire us to protect them. Every effort to preserve their habitats, mitigate human impact, and educate the public about their vital role ensures that the silent, watchful eyes of nature's perfect assassins continue to patrol the night, a timeless testament to life's ingenious adaptations.